In this video, we're going to do an abbreviated review of trigonometry, and in particular, how the sine and cosine functions relate to standard triangles, and then also going to the unit circle definition. If it's been a while, please do review trig on your own. This will be a very quick review. In particular, remembering the mnemonic SOHCAHTOA, which tells you the relationship between sine, cosine, and tangent, and the opposite hypotenuse and adjacent hypotenuse ratios. Two triangles that come up a lot in working with trigonometry, especially in math classes, are the 45, 45, and the 60, 30 triangle. In these triangles, remembering they might be expressed in radians. Pi over 4 is 45 degrees, pi over 3 radians is 60 degrees, and pi over 6 is 30 degrees. When we're looking at trigonometry, what we have in these triangles, I'll use the Trig Radians here, we can build through Pythagoras a triangle that has sides 1 and 1, which is nice and convenient, and then if you use Pythagoras to find the hypotenuse, you get root 2, and from that you can easily find the trig values. In fact, I don't actually remember these rules here. I just draw the triangle and then do the calculations as needed for the trig functions we're working with. But if we are asked for the cos of pi over 4, that's adjacent over hypotenuse. And if we're asked for sine of pi over 4, that is opposite over hypotenuse, which turns out to be the same thing for the 45-45 triangle. In the 30-60 triangle, the easiest way to remember this, I find, is to take an equilateral triangle with side lengths 2 and then cut it in half to get the 60-degree angle here, or pi over 3, the 30-degree angle here, pi over 6, and then ignore this triangle and focus on this side here. If you use Pythagoras, you'll find that this vertical side has length root 3, and from there we can find the ratios we're interested in, such as cos of pi over 3 and sine of pi over 3. If this is our base angle here, the cosine is a half, 1 over 2, adjacent over hypotenuse, and the sine is the opposite over hypotenuse, root 3 over 2. We can then also do the same calculations for the pi over 6 angle. It ends up just being the opposite order. Cos is the adjacent over hypotenuse, that's the root 3 over 2, and then the opposite over hypotenuse for sine gives us 1/2. We expect that students will be able to recognize when they have these kinds of angles and then be able to come up with fractional versions of the sine and cosine of those angles based on these kinds of triangles. Working with these fraction forms rather than a long decimal version of this turns out to be very useful in avoiding complications and allowing us to cancel and simplify expressions. So do have these at your fingertips as you work with trigonometric functions. When we look at triangle ratios, as our definition of trig function, sine and cosine, where it's opposite over adjacent or opposite over hypotenuse, adjacent over hypotenuse, the limitation that we quickly encounter is we can only talk in triangles about angles from 0 degrees to 90 degrees, and in fact, you can't really even go to 90 or 0. There's an easy way to extend the definition, though, so it works for angles that are of any magnitude. And the way we do that is extend our definition of the trig functions to the x location and y location based on an angle. So we have an angle, and when we pick a point on this unit circle which has radius 1, if we measure the angle from the horizontal axis around to that point, the point we're at will actually give us cos theta and sine theta. That doesn't seem intuitive at all at first until we look at how we can build those coordinates as distances from this origin, either in the x direction or the y direction. Cos of theta and sine of theta here. When we do that, and we imagine what we get as the coordinates, let's say the y coordinate first, as we move from here, the y coordinate is 0. So if we graph the angle, so imagine this green line is our angle. When the angle is 0, what do we get as the, let's do this in blue for the y coordinate, which I'm claiming is sine of theta. Well, we get a 0 value to start. When we get up to pi over 2, or 90 degrees, the y-coordinate we're at then ends up being 1. So let's make an axis here, 1, pi over 2. When we go to a full 180 or pi angle in radians, we're going to be back down to a 0 y-coordinate. So if we're just looking at the vertical component as we go around the circle, we're going to see this kind of pattern. And if we sketch that out, we get what we think of as the sine function in a graphical sense, where as the angle increases, the y-coordinate of the blue dot as we move along here, and then goes negative, and then goes to 0, then goes to positive, it'll trace out this single axis graph. Notice we can also go negative in that sense too, and that will give us this graph also defined for negative angle values. We can talk about angles below 0. If we repeat the same idea, just with the x-coordinate, and imagine tracing out the same dot, notice the x-coordinate starts at 1 if we look at the x, and then it goes to 0 when we hit 90 degrees as our angle, and then it goes down to, then it goes all the way down to x equals -1, and we start to see almost the same pattern, just in a different location, and it turns out that that's going to be the graph of cos of x. Now there's a few nice properties we can infer from this. The first is, using the circle definition leads very quickly to understanding our trig identity about sine squared and cos squared. If we have our circle, and we take any point, and we take the angle to that point, what we're claiming is that we define this vertical axis here. Let's do this in a different color. This vertical distance, which is the y-coordinate, is sine of theta. So this distance here is sine of theta. This distance here on the axis horizontally is cos of theta, because the x-coordinate at the point we're talking about is cos of theta. So our point is cos theta sine theta, and that means these distances are sine theta cos theta for the horizontal and vertical distances. Well, as soon as we say that, and we know we're on the unit circle, which means the radius is always 1. Wherever we draw these lines, it's a circle. Because the distance to this point is always 1, we can pull out Pythagoras, and we'll have that sine squared theta plus cos squared theta. Those are the two sides of a right angle triangle. Those are always going to add up to the hypotenuse side squared, but 1 squared is just 1. So sine squared theta plus cos squared theta equals 1 as a fundamental identity of the trig function sine and cos. We can also tie that back to the original triangle definitions through the same kind of mechanism. If we pick a point that's in the quadrant from 0 to 90 degrees, and we draw a right angle triangle based on that, we know that this side here is 1, and let's call this the adjacent and the opposite for this angle here. Then we know that cos of theta is adjacent over hypotenuse. Oh, well that just means that this side length, A, is the same thing as cos theta. So we can literally write this distance here as cos of theta. Meanwhile, the opposite follows the same idea. If we take sine of theta, we have the opposite over 1, or just the opposite side. It's on 0, it's a big O, it's hard to tell. But we're going to erase it right now and recognize that it's going to convert to or be equivalent to sine of theta. And that goes back to our idea that the x-coordinate, well, that's the distance from the x-axis, that's cos of theta, and the distance in the y side, or the length of this side here, is sine of theta. So whether you think of this as triangle angles, opposites, and adjacents and hypotenuses, or whether you approach this as a unit circle with the point being defined by x as cos, y as sine of the angle. They both give you the same values when we're working with both of those versions for the standard triangles. So we can see that on this interval here of angles 0 to 90, they're exactly the same, the triangle definition and the unit circle definition. And then the unit circle definition gives us one way to extend that to angles that are smaller than 0 and larger than 90 degrees. It's useful to have both in mind. Sometimes one becomes more important in a particular question than the other.